part 3 of lecture 4. In this part, we will talk about regularization. And before I talk about that, I want to talk about what the problem is. Why do we need to do this? And the problem here is, suppose we have a deep neural network with like more than 2 layers and sufficiently large number of hidden units, then we can fit any training set perfectly. I remember we talked about this in the previous lecture, that it can approximate any continuous or not continuous function arbitrarily close. So we can fit any training set using basically any arbitrary classification boundary. So suppose we have, say, cats like this, and let's say these are dogs. So there's one particular like very strange cat, and what a neural network can do is it can fit this boundary like this, and it may not be what we want. We may want something that's simpler and generalizes this better. So we're calling these kind of things generalization error, and it comes from if in the test set we have a dog image that's like here, well, it's more likely a dog. So we do not want our neural network to fit this training set too closely. We want a simpler and more general function classification boundary, or more general neural network. So that would be our goal, simpler and more general. So this problem of fitting the training set too closely is called overfitting. And I have the diagram already, but there is a better diagram from Wikipedia, this one. And here, the green decision boundary is overfitted. So we want the model, we want our neural network classification boundary to be something like the black curve. But if we train long enough, or if we use a very complicated network structure, we can actually get this overfitted thing, which is not great. So when we actually have, say, a dot here, I think it's more likely to be a green dot than a red dot. So this red dot may be just an outlier. So there are many ways of fixing this. I will talk about 4 of them, and they are like completely different. So you can combine them and use any combination of these methods. So the first one is using the validation set. So in lecture 1, I talk about validation set briefly, and it's basically a small set that we split from the training set, and we use it for testing. So because the training set data are labeled already, so the validation set data will be labeled as well. So we just use it as a test that we know the answer of, basically. So we will use this subset of the training set to actually train, and use the other set to just evaluate how good the model is. So let me use a diagram to explain this. So this is the number of iteration, and this is our cost. So as I said, if we train and train and train, we will eventually reach 0. And 0 means we are overfitting, we are fitting the training set too well. However, if we have an independent different validation set, at the beginning will be large, but if we train and train and train, it will not get better and better. At some point, it will be worse, because at this region, it will be overfitted to the training set. So it's not as good in the validation set. So what we can do here, obviously, is we can stop early. So if we stop when the validation set costs begin to increase, then it performs good on the validation set as well as the training set. So if we stop here, the result might be more general because at least it's having a low cost. So this line actually represents the cost on the validation set, the instances in the validation set, and this is the cost of the instances in the original training set. So if we stop here, then the cost is low for both of the sets. So we may want to do that. So that's one way of regularization. And the second one is a completely different one. It's very specific for neural networks. And the idea is basically we can drop out a random subset of the units in a neural network. So, suppose we use a probability of 0.5, then we basically remove a unit with probability 0.5. And at the end, we need to rescale this. And the scaling is kind of complicated if we use kind of the different probabilities. So I will not talk about actually how to do this mathematically. But the main intuition is that if we are constantly dropping off stuff, then a hidden unit would work with different combinations of other units, because sometimes during the training it is there, sometimes it is not there. So basically, every unit will work independently, but not depend on some combination of the other units. So it means each unit will be individually useful. And why is this model better is because if we have multiple units really dependent on the other units working, then we have an unnecessarily complicated model. I don't know how to spell unnecessary. Unnecessarily complicated model if they really rely on other units. But if they are individually useful, then we have basically the simplest model using this set of units. So the WY, it kind of solves the regularization problem and well, overfitting problem, and it's a regularization technique. So if you want a diagram, so suppose you have two input unit and you have three hidden unit, and we have say just one output unit, then in the first few iterations, we cannot just do one iteration and switch. That will mess up the training. So in the first like 100, 1000 iterations, we use these two. So we set these weights as constants, and also we don't need this weight. And maybe after 1000 iterations, we switch. We change to these two. Then what it means is how this particular unit works does not depend on the fact that that one is working, and also it does not depend on the fact that the other one is working. So this is basically working independently to do the best job. So the resulting model, as I explained, will be a bit better and more general. So the third method is actually the most popular one. And when people talk about regularization, actually they mean just L1 and L2 regularization. So it's basically the most popular and most important one. And the basic idea is we want weights that are zero. So if some of the weights are zero, it means if you look at this W2 plus B, if say W2 is 0, then the model only has one feature, and it's a lot simpler, right? So same for a neural network. So if the weights are 0, then you don't have the weights, then the neural network structure is a bit simpler. So here, suppose we are talking about a logistic regression, it means only feature 1 is important, feature 2 is not important. So we can get rid of this unnecessarily complicated feature, and we have a more general model as a result. If we try to make some of the weights 0, and of course we cannot just force some of them to be 0 because we don't know which one should be 0. So what we will do is include these weights as a cost. Right, so if we look at our one regularization, we use the one norm. So what I mean by one norm is just the sum of absolute values. So you don't need to worry about this line. We're just saying if we have a larger weight, then it's a larger cost. So basically the total cost is the number of mistakes plus some regularization parameter, lambda, multiplied by the size of the weights. So larger weights would incur a cost. So when we want to minimize the cost, we want to minimize the mistake, and also we want to minimize the size of the weights. So we want smaller weights, basically. And one thing, if you are from the statistics department, you may heard of lasso. And lasso is just linear regression, but basically this square arrow with no activation function with L1 regularization. So that's lasso. And L2 and L1 are very similar. The only difference is there's a square. So in particular, there's a square here. So instead of absolute value, we just square them. And we're still having to minimize the number of mistakes and minimize the size of the weights. And it's just we define the size differently. So L1 regularization will lead to more weights that are exactly 0. So when they're exactly 0, it means they are not important at all, so it's useful for feature selection. So some features are not important, so we can get rid of them completely. Because when weights are exactly 0, we don't actually need them. And L2 regularization will lead to a lot of weights being close to 0, but not exactly 0, so we cannot really drop them, so we still need to keep them. But why is square good? Well, gradient descent. We can differentiate it. L1 is the absolute value. Absolute value is not differentiable by 0. So we'll talk about using subgradient in the next lecture, but it's not really relevant here, so I'll not talk about it here. So one way to compare L1, L2 regularization is using L1 and L2 norm. So let me draw a diagram and briefly talk about it. So suppose the cost function, suppose the cost function goes in that direction. So basically we have lower cost here and we have higher cost here. What kind of points would have the same sum of, say, absolute value of the weight and the bias? So say the constant is 1, then it will be this. Right? So here will be 1, here will be 1. So if you look at this shape, every point on this shape would have the sum of absolute value of W and B equal to 1. You can try it. So here is 0.5, 0.5. The absolute value sum is 1. And here 0.5 minus 0.5 is also 1. So it turns out that along this diamond shape, it's all constant. And similarly, 2 would be this diamond shape here. And if we want to fix the level of C, so for a fixed C, if we want the largest weight and bias sum in terms of absolute value, let's see, I think it's this one. Let me only draw half of it. And the point of intersection has W equal to 0. So if we imagine the C slope slightly differently, we may be hitting that point instead. So it's highly unlikely that we hit something in the middle. It's more likely that we hit either B is 0 or W is 0. So this is the intuition why in the previous slide I said L1 regularization would lead to some of the weights being exactly 0. And if we look at W and B, and maybe the same cost structure going lower that way, and if we think about fixing our cost level here, and we have a constant level of B squared plus W squared, which are circles, we usually hit here. And here it's not this B0 or W0. So the expression here is W squared plus B squared is constant. So that'll be why we are getting kind of good weights, but they are not exactly 0. So from my experience from last year, people who are not familiar with Lagrange multiplier stuff do not understand what I'm talking about here. So that's okay. So if you know Lagrange multiplier when doing optimization problems, I think you can understand this already. But if you don't, then it's not an important thing. You can just remember the result that L1 regularization lead to something that's exactly 0 and L2 does not. So that's the important result that you should know. And next one, and the last one that I'll talk about is called data augmentation, which means we are just increasing the number of training points. So of course we're not just adding new training points because we don't have them. So we can create some of them from the existing ones. So for example, for programming assignment 1, we can translate the handwritten digits and get a new image, or we can even rotate them and get new images that are similar but not exactly the same, and put all of these in the training set so we have more training sample. So that would help. Of course, more training the sample would make the model more general. So the next and slightly different topic that I want to briefly mention at the end is about hyperparameters. So there are some of the parameters in the models that are actually parameters. So the weights and the bias terms are actual parameters. So we are training them, and at the end of the training, they will specify what the model is. However, there are other parameters that we can specify ourselves. For example, the learning rate, especially the initial learning rate, and the stopping rule, which means if the cost difference is smaller than a specific number, we will stop. And we could change that as well. So these are actually easy to choose. You can just try different ones and see which one work. And so it's regularization parameter. It's supposed to have a like intended number of 0 weights, then you can just change regularization parameter and try different things. What is not clear is how to choose the number of hidden layers and number of hidden units. So you can try many of them, but you don't actually know how to compare which one is better, which one is worse, right? So here, these parameters that are not trained, they're called hyperparameters, and we'll talk about how to choose hyperparameters. The answer is mostly still just try different ones and see which one is better. But we need to define what better means. So one particular way to do that is called k-fold cross-validation. So the problem here is if we have a training set, and if we train on the training set, for example, a large neural network, and we test on the same neural network, probably the accuracy will be 100%. Right, so as I talked about, if we train long enough, we can get zero mistake anyways. So basically, if we train and test on the same set, the accuracy will be 100%. So this accuracy is not a great way to measure training set accuracy. And if we just split the training set into one training set and one validation set, we don't get the accuracy on the training set. So that's not a good idea as well. So what we can do is something called cross-validation. So we basically split the training set into k groups, and basically we repeat the same process k times. We train k different models with the same hyperparameter, and then we test it on one of the groups. So we use k minus 1 groups to train. So k minus 1 groups to train. So the parameters will be different, but we want the same hyperparameters because we are comparing hyperparameters, right? So of course the parameters will be different each time we train, but we keep the same hyperparameter, and then we basically test it or validate it on the remaining one group to get, say, accuracy. So if we do this for different set of hyperparameters, we can actually use this accuracy to compare models with different hyperparameters. So that's what we're going to do. And one simple example is, suppose we want a 5-fold cross-validation. Then we split into 5 sets, and then we train on the 4 sets and test on here, so we get the accuracy here, and then we get the accuracy on the second set, third set, and fourth set. So remember, they have the same hyperparameter but different parameters, and we repeat this whole process for different hyperparameters, so we can compare which hyperparameter is better. So to be more concrete, we go through this once with the same neural network structure, same number of hidden layers and hidden units, and we repeat this whole process for different number of layers and so on, and compare the sum of the accuracy. So that accuracy, as the sum of these 5 accuracies, is a better measure of the accuracy on the training set. Noting that if you combine them, it is actually just the training set. So that would define the accuracy on the training set instead of just using all the data and testing on the same data set, which, as I said, they are all zeros, so that doesn't make any sense. So basically, we're using cross-validation to get a better measure of accuracy on the training set. And one special version of k-fold validation is when k is equal to the number of sample in the training set, then each time the validation set contains only 1 point, and this special case is called leave one out cross-validation.